So today we're going to learn about the electromagnetic spectrum and also reflection. So the electromagnetic spectrum was discovered by none other than Newton. And what he discovered was that white light, so right here we got a beam of white light coming in. If you pass it through a prism, it splits into a bunch of different colors. And Newton realized that it wasn't the prism creating the colors. The colors were already present in the light, and the prism was causing them to separate. And you could do clever little experiments like pass this through a filter that removes the blue light from here, and then you could see that the blue light would be absent from the spectrum. So Newton is the guy credited with discovering what we call the electromagnetic spectrum. What he realized is that what we see as white light is really a combination of all the colors. So our eyes perceive all the colors together as white light, but the light itself is not actually white. It's one of several different colors, and together they make white. So 100 years later or so, Herschel is doing some experiments. He's investigating the temperatures that are associated with each color of the spectrum, what you would probably call the rainbow. So we had thermometers in the blue and a thermometer in the yellow and the green and in the orange and one in the red. And by accident, he had an extra thermometer over here on the side that he wasn't using. And much to his surprise, this thermometer over here that was a little past red actually got the hottest. So a prism was splitting the energy from the sun into different frequencies, different colors. And there was something over here that our eyes cannot see, but it was even hotter than red. So Herschel's credited with discovering the fact that the spectrum goes on. There are frequencies that are lower than red. This is called infrared. And there are frequencies that are higher than violet. These are called ultraviolet. We can't see them with our eyes. Our eyes are only limited to a small section of frequencies, but they're still there. So what we now know is that electromagnetic waves come in lots and lots of frequencies, all the way from very slow wiggles of charges, like only 10,000 wiggles per second, all the way up to 10 to the 20th wiggles per second. And all of these waves are the exact same thing. They are electromagnetic waves. So what we call visible light is this little section right here. But other frequencies have other names. We can't see them with our eyes, but we use them. So if you start here at visible, then on the left side, the wavelength is short and the frequency is high. So violet light has the highest frequency of visible light. And as we move to the right, the frequency gets lower. So red has a lower frequency and therefore a longer wavelength. Below red is infrared. This is primarily the waves that carry the heat to us from the sun. Below infrared is microwaves, and this is the section here that we use for communications. Then we have radio, and on the other side we have ultraviolet. X-rays are just electromagnetic waves, except their frequencies are so high they can only come from nuclei. And then gamma rays. So these things are all connected. They're all different frequencies, and we call all of these frequencies together the electromagnetic spectrum, of which a very small slice is the visible range. Now, if we focus on this section right here, the communication section, there's a trade-off. There's different frequencies. So we have long radio waves, medium radio waves, we have FM radio waves, TV, GSM, which is like GPS, 3G, 4G, 5G, your Wi-Fi, satellite broadcasting. These are all in this range right here. And there's a trade-off. In this diagram, on the right-hand side, the frequency is increasing. And as the frequency increases, the wave can carry more information. But it doesn't go as far, so you have less range. On the other hand, over here, the waves don't carry as much information. We call that decreasing bandwidth. They don't carry as much information, but they reach really far. So, for example, shortwave radio can reach all the way around the world, but you can't have very much information transmitted per second on it. So the sweet spot is this area right in here. So this area right in here is primarily what we use for communication. It's where your TV and your satellite phones and everything work. It's sort of a nice trade-off between high speed, lots of information, but not having um, too small of a range. So when you listen to the news and you hear about a company like AT&T spending $20 billion for a new slice of the spectrum, what they're buying is the rights to use a frequency somewhere here in this range. And each of these frequencies is assigned to companies who pay to use them, and the FCC regulates them. So if you want to start a new radio station, you have to apply for a license, and they tell you what frequency you are allowed to use. You can't use somebody else's frequency. So that makes for some interesting debates. You've probably heard about that in the news. All right, so this electromagnetic spectrum is all of the frequencies, starting from the highest frequency, which is gamma rays, down to the lowest frequency, which is radio waves. And visible light is somewhere in the middle there. Okay? All right, now when we talk about waves, waves look like this. They go up and down. This is like the electric field. And we think about the wave direction as moving to the right. This green arrow shows the velocity of the wave. We can draw a wave coming out of a laser like this. So this is like the red part is the high parts of the wave, and then the black is the low parts of the wave, and then the red is the high parts. So you can kind of draw like that. But typically what we do is we represent this entire wave as what we call a ray. We're just going to draw a single red line here, put an arrow on it if it's moving to the right, and we're going to call this a ray. So when we talk about a ray of light, what we really mean is sort of a representation of the entire wave and the direction it's going. Now, when we send a beam of light and it hits a surface that has lots of free electrons, that wave can be reflected. And if we measure the angle of incidence, this angle, and we measure the angle of reflection, we get an easy relationship. This is probably the easiest relationship in physics. If I have a shiny, smooth surface, the line that's perpendicular is normal. I have an incoming ray of light. It reflects, and this is the angle of incidence. This over here would be the angle of reflection. It turns out that those two angles are exactly equal. The angle of incidence always equals the angle of reflection. Now we talk about refraction, and that's different. So this is reflection. All right, that's the law of reflection. We're not going to solve any problems with it because it's kind of boring. Here's an example of reflection at work, though. Here is a chateau in Canada at Lake Louise, and this is what the reflection on the water looks like when the surface of the water is very smooth. And this is what it looks like if there's a little bit of wind making the water choppy. So here we have a perfect reflection because the water is smooth. Here we have imperfect reflection because the water is rough. Here's what's going on. In a perfectly smooth surface, like this is perfectly smooth, the light hits the surface and they all bounce in the same direction. Okay? So this is what we call specular reflection. On the other hand, if the surface is rough and bumpy, although each individual ray of light obeys the law of reflection at the point that it hits, because the surface is irregular, these light beams bounce all over the place. They're scattered, and we call that diffuse reflection. So in our picture here, this is specular reflection. You can see an image. And this is diffuse reflection. You can kind of make out a little bit of an image, but the light is being scattered all different directions there. So specular is sort of perfect reflection, and diffuse is random or chaotic diffusion. So maybe when you've been driving your car, you've noticed that your headlights bounce off the road, and some of the light comes back to your eye, and you can see the road in front of you. That's true when the surface is dry and rough, but when it gets wet, the surface gets smooth, and instead of the light diffusely reflecting, it reflects in a specular manner, and almost all the light from your headlight bounces over in this direction. So when the road is smooth, you might notice that it doesn't seem like your headlights are working as well. Not as much light is bouncing back to your eye, like here. And in addition, the guy over here coming towards you feels like your headlights are brighter because none of the light is bouncing back. It's all bouncing right towards her. So this person over here feels like the lights are super bright, like your high beams are on. So when you're driving at night next time and it's raining, pay attention to what kind of reflection is going on. A piece of paper reflects light and it looks white, But the reason it doesn't look like a mirror is because microscopically, this is what paper looks like. It's a big mess. Paper is basically just wood fibers that have been milled and smooshed together. And so under a microscope, paper looks like this. And so you can imagine why paper doesn't cause specular reflection. You can't see a reflection in paper. Even though paper reflects all the light that hits it, it goes in all different directions. And a mirror is an example of specular reflection. So the light that hits that mirror bounces off and returns to your eye, and it forms an image. So we'll talk about image formation later, but specular reflection leads to image formation in mirrors. Now, light has a dual nature. It's both a particle and a wave, and this is really one of the deep mysteries of nature. How does light have both a wave and a particle nature? We are going to stick to the wave nature of light. The particle nature of light really only exhibits itself in quantum mechanics, and that's way past the scope of this class. So we're going to talk about the things we can understand with the wave properties of light, and that's all we're going to limit ourselves to in this course. So since we're talking about light as a wave, we can use all of the stuff we learned back in the unit on waves to apply to light. Waves can be characterized by their frequency and their wavelength. And so back in Unit 7, we talked about wave equation. The velocity of a wave is equal to the frequency times the wavelength. When we are talking about light, we still have a frequency, we still have a wavelength, but the velocity is known. It's the speed of light, it's c. So our equation for light waves looks a little different. Instead of v, we put c here. But the speed of light always equals the frequency times the wavelength. And so for your problem set, you're going to solve a couple little equations with this, a couple little problems with this equation here. So let me do a quick example. Suppose we have a microwave oven, and the back of the microwave oven tells you that the frequency of the waves is 2.45 gigahertz. I want to know what is the wavelength of this wave. So to solve that problem, here's my diagram. I know the velocity of the wave is c, which is 3.0 times 10 to the 8th, and I know the frequency is 2.45 gigahertz. So that's 2.45 times 10 to the 9th hertz. I'm trying to find the wavelength. So I'm simply going to solve my wave equation for the wavelength. Remember to make a lambda. We practiced that back in Unit 7. Lambda, the wavelength, will be v over the frequency. Plug in our numbers, and you get 0.118, or about 12 centimeters. So the wavelength of the microwave waves is about 12 centimeters. Okay? So that's how you can solve problems. And you're going to solve some problems using this equation and solving some of it. That's going to be your problem set for your e-learning tonight. And you don't have to show solutions for these. You're just going to do the calculations and put your validation code in online. And that will be your lesson for Tuesday here. Okay? All right. Good luck.